And now we turn to Quantum Tomorrow, and the speaker is Deborah Jin from NIST. And we'll have to transfer the microphone. And since this talk was Quantum Tomorrow, her title will only be revealed in her talk. I see John's quantum computer is entangled. We'll relieve you of your duties. Ah, there we go.
Okay, thank you very much. Can you hear me okay? I'll be talking about quantum gases of atoms and molecules. These are ultracold gases. I'm from Gila, just down the way in Boulder, Colorado, although it was a long commute this morning. The outline of my talk is I'm going to give you some introduction to ultracold gases, what they are, thinking about them a little bit in the context of this session on the 100th birthday of Bohr's model of the atom, and a little bit on why we're studying these gases. I'll tell you just in a few slides how we create them. I'll talk a little bit about interactions between particles in these gases, which turns out to be really important. And then I'll try to, at the end of my talk, just highlight some recent work that we're doing in Boulder, Colorado, where we're making ultracold gases not of atoms, but now of molecules. So let's start with thinking about ultracold gases. So this is a session on the 100th anniversary of Bohr's model of the atom, or the quantum atom, where he introduced these quantum rules for the orbits of the electron around the nucleus in the atom. And so this introduces the idea that particles can behave like waves, that you have massive particles have a quantum wavelength or a de Broglie wavelength, which is just given by Planck's constant over the momentum, the mass of the particle times its speed, v. Now, we call this the quantum atom, but if you really think about it, what's quantum here is really the electron. It's the electron behaving quantum mechanically inside the atom. So in the quantum atom, it's really the electron that follows quantum rules. I want to talk about a system where the atom itself is quantum. That'll be a gas of atoms where the atoms themselves follow quantum rules. Okay, so this is along the ideas that John mentioned of extending quantum mechanics to larger systems, more macroscopic system. An electron has a pretty large de Broglie wave because its mass is very small. If you think about an atom will be typically 10,000 times heavier than an electron. So this mass is 10,000 times larger. The de Broglie wavelength is 10,000 times smaller. And so usually atoms, heavy objects, don't follow quantum rules. In fact, the requirement that the atoms inside a gas follow quantum rules, or at least that has an important impact on the behavior of the system, is that this de Broglie wave has to be as large as the spacing between particles. This is some average spacing of particles in a gas. Now, a gas is a low-density state of matter, and we work in these ultracold gas experiments with especially low-density gases. So this distance between the particles d could be like a micron. Okay, so we're talking about trying to make a massive object, an atom, 10,000 times heavier than the electron, have a de Broglie wave of a micron. Okay, so obviously that's typically not the case. When we think about gases, we usually use a very classical kinetic theory of the gas. We picture a gas as little particles bouncing around. Now, I've just drawn the atoms here as just these balls, and these arrows are the velocity or the speeds of the atoms. But we know that the temperature is connected to the kinetic energy, so we can lower the speed of these particles if we could lower the temperature. But let's just look at room temperature. So that's 300 Kelvin, just measuring from absolute zero. The speed of the atoms or molecules in the air around us we know is jet airplane speeds. So hundreds of meters per second, about like that. So if you plug that into the formula for the de Broglie wavelength, just Planck's constant over the mass of the atom times its speed, you get that the de Broglie wavelength of the atom is 0.3 Bohr radii. So the Bohr radii is the size of the atom. So you've got a de Broglie wavelength smaller than the radius of the electron orbit. Okay? So obviously this quantum mechanical behavior won't be very important in this gas, and this classical picture works very well at any temperature that you would probably think about normally. So how cold do we have to get to make a quantum gas, to make the atoms behave quantum mechanically? We need to reach temperatures of something like 100 nanokelvin, so a tiny fraction of a degree above absolute zero. So here's my picture of the ultracold gas. You can tell it's cold because this guy's got a hat and a scarf, and he's got ice on the thermometer. And if you'll notice, these particles are moving much slower. So I drew these arrows much shorter. So we know, just going back to this relation, if we lower the temperature, we'll lower the average speed. Okay, plugging in 100 nanokelvin now, you get that the atoms move about this fast. So it's snail speeds, a few millimeters per second instead of the hundreds of meters per second that the molecules in the air around us are moving. Okay, now I can plug that speed into Planck's constant over mass times speed to get the de Broglie wavelength, and I can get a de Broglie wavelength here that will be 20,000 times the Bohr radii. So 20,000 times larger than the size of the atom. Plug in numbers, this is about a micron. This is large enough to be comparable to spacing between particles, even in a low-density gas. All right, so that's the condition you need for a quantum gas, a gas where the atoms themselves behave quantum mechanically or follow quantum rules. I want to give you just a sense of scale on temperatures here, how to think about 100 nanokelvin. So here's a log scale thermometer marked in Kelvin. Each number here is a change of an order of magnitude. Here are some things you might be familiar with in nature. Here's the temperature outside right now, a few hundred Kelvin. Going up in temperature, here's the temperature of the surface of the sun at several thousand Kelvin. Going down in temperature, the lowest temperature you find in nature is a few Kelvin. Okay, that's about here. Now in the laboratory, we can reach temperatures much colder than you can find in nature. For example, down here is a millikelvin. A millikelvin is a very standard temperature to reach with a big refrigerator full of liquid nitrogen and liquid helium. A so-called dilution refrigerator can easily go down to a few millikelvin. But we talked about for the quantum gas, we need to go down to hundreds of nanokelvin. That's another 10 orders of magnitude colder down here. We can't reach that with this kind of technology. Yet that's where we're going to create the ultracold gas that's quantum mechanical. Okay, before I move to telling you how we do that, extremely briefly, I want to talk about why. First, let me give you some numbers. I told you the temperature. The system we can create in the laboratory is actually a very small amount of this gas. It will have only maybe 1 million atoms in this gas. It'll be in some kind of container, obviously, in ultra-high vacuum. And it'll have a particle density of about 10 to the 13 particles per cubic centimeter. That's 1 million times less dense than the air around us, so it's a relatively low-density gas. And the spacing between particles, again, for this kind of density is about a micron. Okay, so why do we want to create this thing in the laboratory? Well, it has a number of uses. People are using ultracold gases for precision measurements. For example, you can measure transitions within the atom extremely well, which means you can make atomic clocks or frequency standards. This is the basis of our GPS, for example. You can imagine that such a system of atoms would be extraordinarily sensitive to any fields, magnetic fields, motion, rotation, etc. And so you can make sensors out of these cold atoms. And they're also a platform that can be considered for quantum information or quantum computing, quantum simulation, etc. that we just heard about. I want to talk about a different motivation, another motivation that really has to do with basic science or advancing understanding of quantum systems. So if we go back to what John talked about, it's very interesting to look at systems of quantum particles where you have many particles, like 1 million particles interacting. And we know this even from the Bohr model of the atom, because Bohr's model worked extremely well for hydrogen, predicted the spectra, predicted how light interacted with the hydrogen atom or ionized helium. But those are systems where you only have one electron, one quantum particle. If instead you pick an atom that has a lot of electrons and you try to understand its spectra, the Bohr model simply doesn't work. I mean, it's not even close. So the point is simply, if you have many interacting quantum particles, you've got a system that cannot be understood just by saying you have a million copies of a single quantum particle. Okay, and you get new kinds of behavior. So, for example, if you take these ultracold gases, and now I'm going to show you some data from experiments, you can see a new kind of quantum matter in this gas. This is a picture of the Bose-Einstein condensate. This is the data from JILA from 1995 on the first Bose-Einstein condensate, which used a gas of rubidium-87 atoms. So the quantum particle is an atom of rubidium. What you're seeing here are three false color 3D pictures of the gas at three different temperatures. The high temperature here on the left is 400 nanokelvin. The low temperature here on the right is 50 nanokelvin. These are pictures of basically the velocity distribution of this gas. So at high temperatures, you just see a Gaussian momentum distribution. This is just the Maxwell-Boltzmann distribution. At lower temperatures, you get this spike in the center. This represents a bunch of atoms near zero velocity in this gas. This is the Bose-Einstein condensate, and you can see it sitting on top of a uncondensed Maxwell-Boltzmann distribution. At lower temperatures, you have a pure condensate. Just to give you some other examples, with this Bose-Einstein condensate, again, it's many particles. There are interactions between the particles, and that gives rise to a property of the condensate, which is superfluidity. So Bose-Einstein condensate exhibits superfluidity, flow of the fluid without resistance. That means if you take one of these gases, this Bose-Einstein condensate, and you start rotating it, you'll find that it develops all these vortices. These little dark spots are actually holes in the density distribution of the gas. Okay, and around each hole, there's a quantized unit of rotation of the fluid. Okay, and it forms a vortex of these quantized, lattice of these quantized vortices. You can imagine this is a highly non-trivial density distribution for an extremely low density gas. Okay, so it's a kind of interesting quantum many-body behaviors you can see. You can also see matter wave interference of these de Broglie waves of the atoms. This is a picture taken from Ted Hensch's group, an experiment where they put atoms in a trap that was an array of microtraps created by light. So it was a so-called optical lattice. If you release the gas from that trap, now in the velocity distribution, you see all these spikes. This is matter wave interference reflecting that crystal lattice structure that the atoms were trapped in. This happens if the atoms are in a Bose-Einstein condensate or superfluid. If they're not, you don't see the matter wave interference. Finally, you can also cool gases of atoms which have the behavior similar to electrons, namely atoms that are fermions, the other kind of quantum particle. This is a picture from my group where we took fermions and made a superfluid, or another phase transition to a superfluid state, where for fermions, the superfluid requires pairing of the fermions, much like Cooper pairing of electrons in a superconductor. Okay, with that introduction, I want to move now to just briefly showing you a couple slides on how we create these ultracold gases, just to give you a flavor. The powerful technique that really opened this field was laser cooling, first developed for trapped ions and later for neutral atoms. And this laser cooling comes back to this Bohr model of the atom, thinking about what happens when light interacts with the atom. You can excite the electron in these quantum jumps. We basically shine lasers in at this gas of atoms and use the fact that the photons impart a little bit of momentum every time they scatter off the atom to slow the atoms down. If we can slow the atoms down by pushing on them with light, we're reducing the speed that's equivalent to reducing the temperature. Also interesting to note that laser cooling works best on atoms that follow this kind of model, the Bohr model. So you'll find that people tend to laser cool atoms that look like hydrogen. So things like lithium, sodium, potassium, rubidium, all the alkali atoms. Laser cooling is extremely powerful, but it doesn't quite get you to the temperatures you need for a quantum gas. So we usually have a second stage of cooling. We turn the light off because eventually the light heats the gas. We can confine the atoms with magnetic fields or also with far detuned light or optical fields. And then we simply cool by evaporation. The same way coffee cools, we just let the high energy atoms escape and we get a colder gas. We have fewer atoms left, but we can reach, again, 100 nanokelvin temperatures with 1 million atoms. Okay, finally, I want to tell you how we take these pictures of the gas. Here, just imagine an experiment. We go to an optical trap. These are typically used at the lowest temperatures. This is just supposed to show you a focused laser beam, and the atom gas is this blue cloud trapped in the focus there. This is just like optical tweezers. If you focus a laser beam, you can capture dust or anything that's polarizable in there, including atoms. So to measure the gas, obviously we have very little material there. We can't really stick a thermometer in there. So what we do is we just release it. So you turn off the trap. The gas then expands. You'll notice that it falls. Atoms obey gravity. We just aren't used to that because usually the atoms are moving too fast. But what we're interested in the fact that the cloud grew. How did it expand? Because that tells us about the velocity. So after it expands, we take a picture. We shine in laser light that excites these quantum jumps, and we measure the shadow image. So we look at how much light was absorbed, and we turn it into these fancy false color pictures. Okay, so the false color just tells you how dense the cloud was, and atoms here near the center had near zero velocity. Atoms here near the edge obviously had a lot of velocity. So we get a map of the velocity distribution, and that's the same thing I showed you in this data on the condensate, just now made not only color but prettier by making it 3D. I want to show you one photograph of what these apparatuses really look like. If you go into the lab, they basically sit on an optics table that fills a standard-sized laboratory room. Here you're looking at just a small part of the optics table. Across here might be about a foot or so. And what you see is just a bunch of optics, mirrors, lenses, etc. In the center of all this is a vacuum chamber, and the ultracold gas is created in this ultra-high vacuum environment. But what you might notice is that in spite of the fact that the gas will be near absolute zero, nothing you see here is cold. It's all at room temperature. We don't use any cryogenic liquids like liquid nitrogen or liquid helium. Okay, I want to talk a little bit about the interactions between the particles because this is what really makes a many-body quantum system interesting. So these days, if the interactions between the particles aren't there or they're very weak, we actually have very good theoretical understanding of many-body quantum physics, the behavior of interacting quantum particles. But if you make the interactions very strong, you go outside of things that we can describe theoretically. And this is the frontier area in quantum many-body physics, is to understand what happens when you make the interactions very strong. We know in condensed matter physics or material physics, this often results in interesting and even technologically useful properties or states of matter for electronic systems. Now, this frontier area of strongly interacting quantum many-body physics is related to many subfields of physics, including, for example, nuclear physics with the quark-gluon plasma, particle physics, etc. So where do our particular quantum many-body system, where does it fit in here? It turns out that these systems make very nice models. They're extremely clean systems that we can make in the lab. We understand the basic ingredients. They're just neutral atoms. We understand single atoms. We even understand 2 and 3 atoms very well. And we have an enormous amount of control over these gases, their temperature, their density, what atoms we use, etc. And I want to tell you that we can even control the interactions, and that's essential for reaching this regime of strongly interacting quantum many-body physics. So what are the interactions? Again, they're electrically neutral atoms. Basically, they only interact or feel each other when they collide. So typical spacing of the particles in the gas, there's no interaction, but they're moving around, and when they happen to encounter another one, you get this short-range or collisional interaction. In fact, the interactions in this gas are very well approximated by a delta function in the distance between particles. In other words, they really don't interact most of the time until they hit each other. All right, let's go back to the Bohr model. So Bohr considered the electrons inside an atom quantum mechanically, and he said there were these orbits, and each orbit has a quantum unit of angular momentum. Well, now we're thinking of atoms as a whole quantum mechanically. Let's look at 2 that are colliding. They will also have quantized orbital angular momentum. Okay, one's not heavier than the other, so they're really orbiting each other rather than one around the nucleus. But you have quantized orbital angular momentum in the collision, and so we talk about the collisions as being S wave or P wave, depending on how many units of orbital angular momentum, just like we talk about the orbits of the electron being S wave or P wave, D wave, etc. Well, you can imagine when you get the gas very cold, what happens is you're removing all the energy, you go down to the lowest orbit. So S wave collisions, collisions with no angular momentum, are basically the only collisions you'll see in these low temperature gases. Everything else gets frozen out. So a consequence of that, you have only S-wave collisions, is all of a sudden you can see these very sharp resonances and scattering. These are scattering resonances of the atoms. They can be tuned, for example, with small changes of the magnetic field. And you see the resonances because you have only these S-wave collisions, and so you're not washed out by having all these other higher angular momentum collisions. So we can use these resonances in S-wave collisions to control the interactions. We just tune experimentally a magnetic field at a small amount around some magic value. And if we go to one side of the resonance, we get repulsive interactions. We go to the other side of the resonance, we'll get attractive interactions. And we can set the interaction strength anywhere between 0 and infinity. Okay, infinity for the system. And that's what allows us to access the strongly interacting quantum many-body system and see phenomena that can't really be described theoretically with our current tools. This was actually required for the Fermi superfluid phase transition, where here you get the phase transition only when you have pairing of the fermions. That required that we made the interactions attractive, and then we turned up the interaction strength to very strong. So this is an example of a strongly interacting quantum many-body system. Okay, I want to turn now to talking about some work we've been doing the last few years in Boulder, where we've been making gases of molecules rather than atoms. This is pushing again toward extending quantum mechanics or observing quantum mechanics in the lab on more complex systems. So we've talked about looking at quantum behavior of electrons inside an atom, extending that all the way to a heavy particle like an atom. Now we want to extend this to something more complex like a molecule. And we're going to take a sort of modest step here. When I say a molecule, I mean a molecule from the point of view of a physicist. It's just going to be two atoms stuck together. It's not going to be DNA or something like that. That's next. Okay. That's quantum physics of tomorrow. Right now, let's talk about molecules. And molecules, you'll see, are already quite complex. But first, I want to talk about why. And the reason really has to do with interactions. With molecules, we have the possibility to open up new kinds of interactions in our quantum many-body system. Again, I talked about these gases as model systems. If you have new kinds of interactions, you can model new kinds of behavior. So with atoms, we have these contact or short-range interactions. They really only interact when they collide. We can make them strong or weak, attractive or repulsive. We have a lot of control, but we cannot change the fact that they're contact interactions. The atoms cannot feel each other at a distance. On the other hand, if you had a molecule where your two nuclei are different, it can have an electric dipole moment. Okay, so you can apply an electric field, and the electron will prefer to sit around one nuclei more than the other. You get an electric dipole moment, and this means you can have a dipole-dipole interaction that's long range. It means the particles can feel each other at a distance. Now you might say, well, why can't you do this with atoms? Don't they have magnetic dipoles? And so you get a magnetic dipole-dipole interaction, and that's true, but that interaction is still very short range compared to a micron, which is the spacing between particles in this low-density gas. So to get a strong enough dipole-dipole interaction that particles can really feel each other at a distance in a quantum gas, we're turning to polar molecules. So that was our motivation. I want to tell you a little bit about the challenges. So it really comes from the fact that molecules are complex. So starting out as an atomic physicist looking at a molecule, you say, how hard could it be? It's just like two atoms, right? So what was my picture starting out? Let's take a simple molecule. I'll just use hydrogen-like atoms because that's what I'm familiar with, like potassium, rubidium. If I stick them together, I get a bound state. It has a binding energy, so it's lower in energy on this axis than two free atoms, right? Okay, I can look at what is that binding energy, and I'm going to put energies in units of Kelvin. So all I'm doing is taking the energy and dividing by Boltzmann's constant, okay? So I'm not telling you temperatures, just energies. But in units of Kelvin, this binding energy for this particular molecule is 6,000 Kelvin. It's a pretty typical binding energy for a diatomic molecule, and you'll note that that's kind of a large energy if you're used to working near absolute zero. All right, but this simple picture doesn't quite hold true. if you look a little bit more carefully, you'll find that there are a whole bunch of states between this, what I thought was a molecule, and two free atoms, and these are vibrationally excited states of the molecule. So it just comes from the fact that the two nuclei can vibrate or can move. And so you get this ladder of vibrational states, and if you look down here, between not vibrating and 1 quanta of vibration is 100 Kelvin of energy. Again, the energy divided by Boltzmann's constant is 100 Kelvin. Again, huge if you're thinking about absolute temperatures near absolute zero. Well, let's not worry about that. We'll just look at the vibrational ground state, where it's not vibrating. But if we zoom in, we find, oh, the thing can rotate. So now you've got rotational states with a smaller spacing than vibration. Again, the first step from not rotating to 1 quanta rotation for this molecule is about 0.1 Kelvin. Again, enormous energy if you're talking about 100 nanokelvin gas. So let's just look at the lowest rotational state. For full disclosure, I should tell you, if I zoomed in here, I would actually see a whole bunch of nuclear spin states. We typically do experiments in a magnetic field. The magnetic fields we work at, these nuclear spin states would have a separation of something like 38 microkelvin, again, much larger than the temperature of a gas that's 100 nanokelvin. So this is really what molecules look like. And to be clear, I haven't talked at all about electronic excited states. This is all electronic ground state. So this complexity makes it hard to get molecules into the regime where they behave quantum mechanically. So we want to make this gas really cold. We have to control the vibration, the rotation, and the nuclear spin states, as well as the motion of the molecules. You might think, well, why don't you just take some molecules, you can go down the hall to your chemist friends, they can give you the molecules, and then you can cool them with laser cooling, evaporative cooling, all these tricks that we've learned from atoms. But remember, I told you that laser cooling really only works very well if your atom can be described by the Bohr model. In other words, a very simple atom, like it looks like hydrogen. Molecules don't look like hydrogen. Diatomic molecules don't look like hydrogen. And so it turns out that laser cooling is proven to be very difficult for molecules. So in Boulder, we've turned to a different strategy, and other people are using this as well, where we say, okay, we know how to do cooling for atoms. Let's go ahead and then just figure out how to do the chemistry to make the molecules. The challenge here should be obvious. It's the fact that we have this huge binding energy we've got to get rid of. So we're going to have an ultracold gas. It's at 100 nanokelvin or so, but we've got to remove a binding energy that's 10 orders of magnitude larger than the temperature of our gas or the kinetic energy of our atoms. Okay, but surprisingly, this is the strategy that has worked and gotten us closest to a quantum gas of molecules. All right, so here's how we do it. The experiment takes 3 steps because everything takes 3 steps. Step 1, we make an ultracold atom gas. This is something we know how to do. We'll cool 2 kinds of atoms because we want to make these polar molecules, and we chose potassium and rubidium, again, hydrogen-like atoms. We cool them down to a few hundred nanokelvin. Step 2, we make some molecules. This actually is also not the hard part because I already told you we know how to control the interactions. So you can imagine if I make the interactions attractive, and I start turning up the interactions from weak to strong, some reasonable fraction of these atoms will pairwise find themselves into a molecule state or bound state. Okay? You're just making them attract each other more and more. This step is not that hard, but it doesn't actually do very much because the molecules you make this way are extremely weakly bound. Their binding energy is tiny, which means they live up here. They're very highly vibrationally excited state. And in fact, the binding energy is so small that these molecules would only exist in a gas near absolute zero. These molecules have no dipole moment. They don't have this electric dipole moment we were after, and you can imagine they're not very stable against collisions. They collide with anything, and they just fall down this ladder of states, which is a huge amount of heating, okay, and not compatible with an ultracold gas. So our third step is we have to move the molecules from this highly vibrationally excited state all the way down to the ground state down here. This is the hard step. This is where we have to remove this gigantic energy, this energy that's 10 orders of magnitude larger than the temperature of our gas. Okay, so we can take inspiration, again, from the Bohr model where he looked at electronic excited states. So far I've ignored those, but of course the molecule also has electronic excited states. It's not quite as simple as that. There's a whole ladder of electronic excited states. But you can find one, and you can use a laser, just like here. You can send in light, and that light can cause a quantum jump from the electronic ground state to some electronic excited state here. So the molecule's absorbed a photon. Now you want it to emit a photon by going back down to electronic ground state, and we're going to tell it to emit a photon such that it goes down to this ground state of the molecule. So we know that the photon energy is set by this energy splitting of the states. So we just put in a blue laser that has a frequency such that it corresponds to the energy splitting between this electronic excited state and not this state, but the vibrational ground state. Okay? This is stimulated emission. This molecule emits a photon into the laser beam, same frequency, same momentum, same direction, and the molecule goes down to the ground state. There are a few other tricks in this. This has to be done fully coherently in order to work well, but the basic trick is shown in this cartoon. Is that the light has removed this binding energy. Each molecule absorbs a red photon or a lower energy photon and then emits a blue photon or a higher energy photon. So that photon carries away the binding energy. Again, if we play these tricks where this can be done fully coherently, we can do it with about 90 to 95% efficiency, and we observe no heating in a gas that's at a couple hundred nanokelvin. The result is we can make now an ultracold gas of molecules. Something like 40,000 molecules is our record. These have an electric dipole moment that are a temperature of a few hundred nanokelvin and a density of 10 to the 12 per cubic centimeter. And all of these numbers were not quite as good as ultracold atom gases, which can have as many as 1 million particles, could be 10 times colder, and maybe 10 times more dense. On the other hand, if you compare it to any previous result on ultracold molecules, you'll find it's 1,000 times colder and 1 million times more dense was this result with this strategy. And this really puts us with these numbers, temperatures, and densities right on the threshold of a quantum gas of molecules, where the molecules themselves behave quantum mechanically, and it matters if they're bosons or they're fermions. Down here, this is just showing one of these false color shadow images of this ultracold gas of molecules. So where are we now in these experiments is that we're just now in the lab beginning to see the effects of these long-range dipole-dipole interactions in this ultracold gas of molecules. That's work going on right now in the lab. I'm going to actually conclude here, and just the conclusion is I've told you a story about taking quantum mechanics from thinking about electrons inside an atom all the way to thinking about an atom quantum mechanically and even a molecule quantum mechanically. By the way, this hand here is not mine. Obviously, these experiments are done by young, active, motivated people. There's some examples of the members of my group currently doing experiments in ultracold atoms and ultracold molecules. I also want to acknowledge my colleague, Professor Jun Yi. He and I jointly lead the experiments that are working on ultracold molecules in Boulder. With that, I thank you for your attention and happy to answer questions.
So we have time for a few questions. And if you go to the microphone, let's see. Does anyone have a... I don't see anyone there. Oh, someone's going to the micro... Oh, we have 2 people now. Or 1 person.
Could you say a little more about how you tune the interactions?
So the interactions are tuned with a scattering resonance. For example, in the Fermi superfluid experiment, we're using potassium. There happens to be one of these scattering resonances at about 200 Gauss, so we just apply a field close to that. We tune the field with only about plus or minus a Gauss or so, and we can change the interactions from 0 to very strong. The scattering resonance is basically means it's a resonance between the energy of 2 free atoms and basically a bound state, a molecular state.
And we have a question on the left side now.
Why is it that you can't stimulate the vibrational energy out of the molecule directly and you have to first excite it and then de-excite it?
Oh, that's a good question. Why couldn't we just go directly down? It just has to do with the frequencies and the coupling. So that would be like a very difficult microwave transition, and also you would have to go down in multiple steps. Whereas the electronic transitions, you have very strong coupling to light, and so it was convenient to go up and down.
And do we have any more questions for the speaker? So if not, let's thank Debbie and the other two speakers for a wonderful session. And I'll remind you that the final plenary session is tomorrow morning at the same time.